Good morning, everyone. I'm Joni, and I hope you're safe and you're making the most out of your time during this community quarantine. So, for today, we'll be answering some problems taken from various chapters from the university physics. So, today, we'll be answering 3 questions from chapter 24. So, let's start with 24.2. The plates of a parallel plate capacitor are 3.28 millimeters apart and each has an area of 9.82 square centimeters. Each plate carries a charge of magnitude 4.35 times 10 raised to negative 8 coulomb. The plates are in vacuum. What is A, the capacitance, B, the potential difference between the plates, and C, the magnitude of the electric field between the plates. So it's important for us to identify our given values, which are D, or the distance between the plates, 3.28 times 10 raised to negative 3 meters, area 9.82 times 10 raised to negative 4 square meters, and charge, which is 4.35 times 10 raised to negative 8 coulomb. Now we also have our constant epsilon naught, or permittivity, which is 8.85 times 10 raised to negative 12 farad over meters. So for the first question, we are being asked for the capacitance. We will be using the equation C is equal to epsilon naught A over D. So we simply substitute our values. We have 8.85 times 10 raised to negative 12 times 9.82 times 10 raised to negative 4 divided by 3.28 times 10 raised to negative 3. And this will be equal to 2.65 times 10 raised to negative 12 farad. For letter B, what is the potential difference between the plates? So we also have our equation for potential difference. V sub AB is equal to Q over C, or charged over capacitance. So we substitute 4.35 times 10 raised to negative 8 divided by the value that we were able to compute for earlier, which is 2.65 times 10 raised to negative 12. So the potential difference between the plates is 1.64 times 10 raised to 4 volts. And for letter C, what is the magnitude of the electric field between the plates? We will be using the equation Q over epsilon naught A. So we substitute the values 4.35 times 10 raised to negative 8 divided by the product of 8.85 times 10 raised to negative 12 and 9.82 times 10 raised to negative 4. So the electric field between the plates is 5.01 times 10 raised to 6 volt over meter. Next, problem 24.14. Figure E24.14 shows a system of 4 capacitors where the potential difference across AB is 50 volts. A, find the equivalent capacitance of this system between A and B. B, how much charge is stored by this combination of capacitors. And C, how much charge is stored in each of the 10.0 microfarad and 9.0 microfarad capacitors. So our given values are potential difference 50 volts, and then we also have the figure here on the right side. So I've taken the liberty of renaming the capacitors as C sub 1, C sub 2, C sub 3, and C sub 4 for our guidance also. So C sub 1 is 10 microfarad, C sub 2, 5 microfarad, C sub 3 is 8 microfarad, and C sub 4 is the 9 microfarad. So for letter A, we are being asked for the equivalent capacitance of this system. So it's important to look at our figure and identify which capacitors are connected in parallel, which capacitors are connected in series. So we first combine C sub 2 and C sub 3 as parallel, and we simply add to get the capacitance between them. So we have 5 plus 8, and we have 13 microfarads for C sub 2, 3. Now to get the equivalent capacitance, we combine C sub 1, C sub 2, 3, and C sub 4 as series. So we get the reciprocals. to get the equivalent capacitance. So 1 over 10 plus 1 over 13 plus 1 over 9, which would give us 337 divided by 1170, and then we get the reciprocal to solve for the equivalent capacitance. And this gives us 3.47 microfarad. For letter B, how much charge is stored by this combination of capacitors? So we can use Q is equal to equivalent capacitance times the potential difference. So we simply substitute 3.47 times 10 raised to negative 6 farad times 50 volts. And this gives us 1.735 times 10 raised to negative 4 coulomb. So this is the charge of the combination of capacitors. And letter C, how much charge is stored in each of the 10.0 microfarad and the 9.0 microfarad capacitors. So we have this explanation because C sub 1 and C sub 4 are in series, which are the 10 and the 9 microfarad capacitors. The charge stored in both capacitors are equal to the total charge. Thus, Q sub 1 is equal to 1.735 times 10 raised to negative 4 coulomb. This is based on our answer from letter B. And Q sub 2 is equal to 1.735 times 10 raised to negative 4 coulomb as well. And then for problem 24.53, in figure P24.53, C sub 1 is equal to C sub 5 is equal to 8.4 microfarad, and C sub 2 is equal to C sub 3 is equal to C sub 4 is equal to 4.2 microfarad. The applied potential is V sub AB is equal to 220 volts. What is the equivalent capacitance of the network between points A and B? And letter B, calculate the charge on each capacitor and the potential difference across each capacitor. So again, we identify our given values, and of course, it's important to look at the figure. So we have C sub 1, there. Alright, so let's start with letter A. What is the equivalent capacitance of the network between points A and B? So we first have to combine C sub 3 and C sub 4 as series. So we get the reciprocals of C sub 3 and C sub 4. So 1 divided by 4.2 plus 1 divided by 4.2. This gives us 10 divided by 21. And then get the reciprocal to get C sub 3, 4, which gives us 2.1 microfarad. Next, we redraw the figure just for our reference and guidance. So as you can see, C sub 2 and C sub 3, 4 are parallel. So we combine them as parallel. So we have C sub 2 plus C sub 3, 4. So this is 4.2 plus 2.1. This gives us 6.3 microfarad for C sub 2, 3, 4. And then again, we redraw the figure so that we have C sub 1, C sub 2, 3, 4, and C sub 5. So we combine them as series, and again, we get the reciprocals. So we have 1 over 8.4 plus 1 over 6.3 plus 1 over 8.4. This gives us 25 divided by 63. To get the equivalent capacitance, we get the reciprocal. So 63 divided by 25 will give us 2.52 microfarad. So this is the equivalent capacitance of the entire network. Now, for letter B, we are to calculate the charge on each capacitor and the potential difference across each capacitor. So you have to expect that it's a fairly long process. So I have placed here a monitoring form so that we won't get confused what are the values that we've already solved for. So we start for the total charge. We start to solve for the total charge first. So Q is equal to equivalent capacitance times potential difference. So this is 2.52 times 10 raised to negative 6 farad times 220 volts. This gives us 5.544 times 10 raised to negative 4 coulomb total charge. Now to solve for Q sub 1 and Q sub 5, since C sub 1, C sub 5, and C sub 234 are connected in series, just to recall, that was the last figure, redrawn figure there. We can say that the total charge is equal to Q sub 1 is equal to Q sub 5 is equal to Q sub 234. Therefore, Q sub 1 is equal to 5.544 times 10 raised to negative 4 coulomb. Q sub 5 is also equivalent to 5.544 times 10 raised to negative 4 coulomb. And Q sub 234 is equal to 5.544 times 10 raised to negative 4 coulomb. So we already have solved for the values of the charge for capacitor 1 and capacitor 5. So for our monitoring form, we've already checked Q1 and Q5. And we've already placed them in the given for our reference. Now, to solve for V sub 1, since we already have our C sub 1 and Q sub 1, we simply divide them, Q sub 1 over C sub 1. So 5.544 times 10 raised to negative 4 coulomb divided by 8.4 times 10 raised to negative 6 farad. This gives us V sub 1 as 66 volts. Same for V sub 5, since we already have C sub 5 and Q sub 5. We simply divide, and this gives us the same answer. So 66 volts. So again, for our monitoring form, we're done with Q1, Q5, V1, and V5. And we've already placed the values on the left side. Now, let's take a look at the other network, which is 2, 3, 4, or capacitors 2, 3, and 4. To solve for V sub 2, 3, 4, we simply divide Q sub 2, 3, 4 by C sub 2, 3, 4. So 5.544 times 10 raised to negative 4 coulomb divided by 6.3 times 10 raised to negative 6 farad. If you're wondering about where did we get these values have been computed from letter A and from our previous computations, and all of them are placed on the left side here, on the left side of our screen. So V sub 234 is equal to 88 volts. Now, this 88 volts will be distributed or will be taken care of by the capacitor C2 and C34. So since C2 and C34 are connected in parallel, as you can see from our image here, we can assume that V sub 234 is equal to V sub 2 is also equal to V sub 34. Therefore, V sub 2 is equal to 88 volts and V sub 34 is equal to 88 volts. So we've computed for V sub 2. We can now compute for Q sub 2. So Q sub 2 is equal to C sub 2 times V sub 2. So 4.2 times 10 raised to negative 6 farads times 88 volts. And this gives us 3.7 times 10 raised to negative 4 coulomb. And then to solve for Q sub 34, we multiply C sub 34 and V sub 34. So 2.1 times 10 raised to negative 6 farads times 88 volts. This gives us 1.85 times 10 raised to negative 4 coulomb. Now, to solve for V sub 3 and V sub 4, since C sub 3 and C sub 4 are connected in series, as you can see from our image, we can assume that Q sub 34 is equal to Q sub 3 is equal to Q sub 4. Therefore, Q sub 3 is 1.85 times 10 raised to negative 4 coulomb, and Q sub 4 is also equivalent to 1.85 times 10 raised to negative 4 coulomb. And finally, to solve for V sub 3, we simply divide Q sub 3 by C sub 3. So 1.85 times 10 raised to negative 4 coulomb divided by 4.2 times 10 raised to negative 6 farad. This gives us 44 volts for V sub 3. Similarly, for V sub 4, we simply divide Q sub 4 by C sub 4. So 1.85 times 10 raised to negative 4 coulomb divided by 4.2 times 10 raised to negative 6 farad. This gives us a value of 44 volts. So looking at our monitoring form, we've already checked everything on our list. So that's our solution. So for our summary of answers, Q sub 1, Q sub 2, Q sub 3, Q sub 4, and Q sub 5. And V sub 1, V sub 2, V sub 3, V sub 4, and V sub 5. Thank you for watching, and I hope I was able to help you out somehow.